morning, dear students. Today we shall see the finite element equations and treatment of boundary conditions. The finite element equations are developed after treatment of boundary conditions. Now, what type of boundary conditions will exist? That also we must see. We know that the total potential energy of the elastic solid is expressed in the form of pi equal to half q transpose k q minus q transpose into f. Here, what is q? Q is the global displacement vector and k, it is the global stiffness matrix. F is the global load vector, right? This is the expression for determining the total potential energy of the elastic solid. Okay, so now, according to the principle of minimum potential energy, the equations of equilibrium are obtained. The equations of equilibrium are obtained by minimizing the total potential energy of the elastic solid. What the principle of minimum potential energy says? Of all the kinematically admissible displacements, those corresponding to the state of equilibrium will extremize the total potential energy. If the extremum of the total potential energy is minimum, then the state of equilibrium is stable, right? This is the principle of minimum potential energy. To develop the finite element equations according to principle of minimum potential energy, we have to minimize the potential energy, right? We have to minimize the potential energy phi according to principle of minimum potential energy. Now, what type of boundary conditions will exist? That we see, right? The boundary conditions are usually of the type, say q p1 equals to a1. This is, one boundary condition. Say q p2 equals to a2, and so on. Say q p3 equals to a3. Say q pr equals to ar. These are the one kind of boundary conditions. I tell you, I take an example and explain, right? Now, I take an elastic solid like this with uniform cross section. This is subjected to a concentrated force P. Okay? When we implement the finite element method, right, according to the basic idea, I divide this into three finite elements: first element, second element, and third element. Okay. Now, where are the nodes? This is the first node of the first element. This is the second node of the first element, right? And this is the second node of the second element. This is the second node of the third element. Okay. Now, this is the first node of the second element. This is the first node of the third element. If you observe here, this solid has a fixed support. Therefore, at node 1, the displacement is 0. Hence, can you write like this according to this convention? Yes, I can write. How I write? I write now as. How can I write? Say here, with respect to this diagram, I can write, say q1 equals to 0. According to this notation, A1 is 0. A1 is 0. I take another solid and explain. Let us see. I take another solid and explain. Let us see. I take a solid like this. This is an elastic solid with one end fixed, right? Now, between the other end and the ground, there is some gap. There is some gap. I say this gap is, say 1 millimeters. 1 millimeter. Right? Now, I implement finite element method. Now, I discretize this domain into subdomains like this. This is first element, this is second element, this is third, this is fourth, this is fifth. Now, nodes are, this is first node, this is second node, this is third node, this is fourth node, this is fifth node, this is sixth node. Now, my element connecting information, element node connecting information is, right? This is the first node of first element, this is the second node of first element. Next, this is the first node of second element, this is the second node of second element. Next, this is the first node of third element, this is the second node of third element. Right, coming to fifth element, this is the first node of fifth element, this is the second node of fifth element, and node 6 is the second node of fifth element. Right? Now, if you represent here the degrees of freedom of all nodes, this is capital Q1, this is capital Q2, capital Q3, capital Q4, and here we get capital Q5, and here this is capital Q6. Right? Here Q1 is 0. So according to our notations, A1 is 0 here. This is A1 because say Q1 equals to A1 and Q2 equals to A2. This type of convention we follow. And Q1 equals 0 to A1 is 0. And here assume that due to self-weight of this solid and other external forces, this end touches the ground. Assume that due to self-weight and other external forces acting on this solid, it touches the ground. Then, what is Q6? Q6 equals to 1 mm. Therefore, according to our notations, this is A6. These are one type of boundary conditions. Understand? So this is how we represent. Understand? And these are the displacements along. These represent the displacements along the degrees of freedom P1, P2, P3 and so on. Understand? Right? How they are specified as say A1, A2, A3 and so on and so forth. Clear? Next. And there are other type of boundary conditions. The type is multi-point constraints of the type beta 1 cube P1 plus beta 2 cube P2 equals to beta 1. Other type of boundary conditions. The boundary conditions will also appear in this form. Okay. So what are beta 0, beta 1 and beta 2? They are the unknown constants. These types of boundary conditions are used in modeling inclined roller supports, rigid connections or shrink fits. These type of boundary conditions are used in modeling inclined roller supports, rigid connections or shrink fits. I explain taking an example. Okay. Now, I have a rigid plane here. Okay. Now, there is a bar of weight W. Right? One end is suspended like this. Another end is suspended like this. This is a material 1 and this is a material 2. Remember, these are the Y's. Both Y's are made of say different materials. If this is a steel, this is a copper. Right? This is the wire made of steel and this is the wire made of say copper. Okay. Assume that a force is acting here like this. Here. A force is acting like this. Once again I draw. Right? This is the rigid plane. Okay? There is a bar of weight W. Right? One end is suspended with a wire made of say steel. Other end is also suspended with a wire made of copper. Okay, now another force, a force is acting here, say P. Right? The point of application of this force is distance say L1 from this point and L2 from this point. Understand carefully. There is a bar of weight W which is suspended from a fixed support by two wires. Both wires are made of different materials. Understand? W is the weight of the bar. And this bar is also subjected to another force P. Then how the boundary conditions will appear? They appear as the multi-point constraints. They appear as the multi-point constraints. Right? In this form they appear. Okay. Beta naught, beta 1 and beta 2 are the unknown constants. These types of boundary conditions are used in modeling the inclined rollers, rigid conductions or shrink fits. Okay. The improper specification of boundary conditions can also lead to, right? Can also lead to enormous results. Two approaches are used for handling specified displacement boundary conditions. They are elimination approach and penalty approach. Two approaches are used for handling the specified displacement boundary conditions, which are elimination approach and penalty approach. Now, elimination approach. So here, to illustrate the basic idea, so we can consider, a problem with a single boundary condition. As I said, you can take an elastic solid with one end fixed and other end is subjected to a force F. Understand? Here, if this is node 1, right, then Q1 equals to 0. Problem is very simple. Because it is a rigid support, here displacement at node 1 is 0. Understand? Displacement at node 1 is 0. If the upper end of the bar is suspended from the fixed support, right, with a known displacement, say Q1 equal to A1, with a known displacement, with say Q1 equal to A1, then how you treat the boundary conditions? You can use elimination approach because it is a known displacement. Okay. Here Q1 equal to 0, it is a known displacement. Here also Q1 equal to A1, it is a known displacement. Understand? And not only this type of axially loaded bar, you can take one-dimensional beam problems also. One-dimensional beam problems also. For example, I take a cantilever with one end fixed like this. It is supporting an endpoint load set P. Right? When I discretize this domain into say two subdomains, this is first element, this is second element, this is the node, and this is the node, this is the node. At this node, remember, deflection is 0. Deflection is 0. It is a known displacement. And slope is also 0. It is a known displacement. Right? And another problem. I take a problem like this. As I said, as I said in the previous example. Now there is a rigid plane at the bottom. Assume that the bottom end touches the ground. Right? Here the displacement is say 1 mm. Assume that the bottom end touches the ground under the action of body force and surface forces. Then, what is the displacement here? At this point, if you say this is nth node, Qn equals to 1 mm. Qn equals to 1 mm. This is a known displacement. Right? Therefore, we can consider the single boundary conditions such as Q1 equal to A1, Q2 equal to A2 and Q3 equal to A3 like that. Right? Right? And we can treat the boundary conditions using the elimination approach. Okay. Now, in this case, I take only one boundary condition, say Q1 equal to A1. Q1 equal to A1. Okay. Now, what is the expression for the total potential energy? Pi equals to Q transpose K, Q minus Q transpose into F. Okay. What is Q? It is the global displacement matrix. It is a column matrix represented like this. And what is F? It is a global load vector which is represented like this as the column matrix. Okay. Now, and what is capital K? It is the global stiffness matrix represented like this. Okay. So here how many degrees of freedom are there in the domain? If you visualize this matrix carefully, with careful observation of this matrix, we can answer there exists n degrees of freedom in the domain. Therefore, this matrix has the size n by n. This matrix has the size n by n. Okay? Right. Well, this is the expression for the total potential energy. Now, we expand this. So, how we expand? Let us see here. Pi equals to half into. So, Q transpose. Right? It is a row matrix. Therefore, a row matrix with elements Q1, Q2, Q3 and so on so forth, Qn into. Next, capital. Right? Capital. It is a matrix of size n by 1, n by n into, again, this is a column matrix. Into, we write a column matrix like this. Q1, Q2 and Q3, Q4 and so on so forth, it is Qn minus, again Q transpose, and it is a row matrix having the elements Q1, Q2, Q3 and so on so forth, Qn into a column matrix having the elements F1, F2, F3 and so on so forth, Fn. Now, what we have to do? We have to multiply these three matrices. So, pi equals to 1 by 2 into Q1, Q2, Q3 and so on so forth tends with Qn. Take these elements, take the row of elements and multiply these elements with the elements of the first column of the global stiffness matrix. Right? Then how you get Q1 into K11. Q1 into K11. You observe here. Q1 into K11. Okay. Into, again, Q1. Therefore, Q. Next, plus. Understand? Next. So, what do you get? Q1 into K12 into Q2. And this is how you can write. This is how you can write. Next. So, minus. Again, Q1 into F1. This is. Next, plus Q2 into F2. This is. Plus Q3 into F3 and so on, so forth tends with Qn into Fn. This is how we write. This is how we write. Okay. After writing like this, what is Q1? Q1 equal to say A1, single point displacement, or single displacement boundary condition. I take single displacement boundary condition. I take say Q1 equal to A1. Then in place of Q1, put A1. If you put A1, what you get? You get like this again. In the same expression, wherever Q1 is there, I put A1. What is A1? It is a known displacement. It may be a zero or non-zero displacement. A1 may be a zero or non-zero displacement, but it is a known displacement. Wherever Q1 is there, I put A. Right? Okay. And sometimes, more than one known displacements we observe. More than one known displacements we observe. Then what you do? That is the question. Okay. Again, I explain. Observe carefully. I come to this. I take a problem like this. There is a solid. I draw a figure. There is a solid of uniform cross section like this with both ends fixed. Now a force is acting here, say P, right? Now how many finite elements do you take? Two finite elements. Up to this one element and this is second element. This is node 1, I say node 1, and this is a node 2 and this is a node 3. So here, how many node displacements are there? Q1 equals to 0 and Q3 equals to 0. Understand? It is a 0 displacement. Then what you have to do? Right? In this expression, you put Q1 equal to 0 and Q3 equal to 0. Understand? If there are non-zero displacements, for example, if there are non-zero displacements, then I say Q1, not in this case. Not in this case, you take a different case, right? And Q1 equal to say 1 mm. Not in this case, take a different case, say Q1 equal to 1 mm and Q2 equal to say 0.5 mm. Then not Q2, Q3 equals to 0.5 mm. Then put Q1 equal to 1 mm and Q3 equal to 0.5 mm. Understand? Then, okay, wherever Q1 is there, I put, okay, 0.1 mm and wherever Q3 is there, I put 0.5 mm. Understand? This is the procedure. Now, we go back to previous case, that is single boundary condition case. So wherever Q1 is there, I put A1. After getting like this, then what I have to do is, I should extremize this total potential energy with respect to Qi according to principle of minimum potential energy. Therefore, here dou Qi of pi, it is not d, it is dou. It is not d, it is dou. Dou by, it is not d, it is dou. Dou by dou Qi of pi equals to 0. Right? Because Q1 is the known displacement. I varies from 2 to n. If Q1 and Q2 are also known displacements, then I varies from 3 to n. Understand? So here, according to principle of minimum potential energy, in this case, how many equations we get? We get n minus 1 equations. N minus 1 equations, not n equations. We get n minus 1 equations. Because here Q1 is a specified displacement. Therefore, we get n minus 1 equations. Now, So how you get the n minus 1 equations? And these are the n minus 1 equations. K22 into Q2 plus K23 into Q3 plus so on and so forth tends to K2n into Qn, which equals to F2 minus K21 into A1. And similarly K32 into Q2 plus K33 into Q3 and so on and so forth plus K3n into Qn, which equals to F3 minus K31 into A1. And ultimately you get Kn2 into Q2 plus Kn3 into Q3 and so on and so forth tends to Knn into Qn, again which equals to Fn minus Kn1 into A. These n minus 1 equations we can represent in matrix form like this. In matrix form like this. Okay. How these are obtained? Observe carefully, because Q1 is a known displacement. Q1 is a known displacement. The first row and the first column are eliminated. The row and column corresponding to the known degree of freedom are eliminated. Thereby they are obtained like this. If Q1 and Q2, are the known displacements, then you have to eliminate their corresponding rows and columns. Of the equations of equilibrium KQ equal to F. And write remaining equations. Because here there are two known displacements. How many equations you get? You get n minus 2 number of equations. Right? When you represent, ultimately you get like this. In the form, say KQ equal to F. Right? Now, I take the equations of equilibrium KQ equal to F and explain with the known displacements. Okay, let us see. And explain with known displacements. Let us see. I take the equations of equilibrium in the form, say KQ equal to F. I write the global displacement matrix like this. Global stiffness matrix like this. K11, K12, K13 and so on and so forth. It ends with K1n. K21, K22, K23 and so on and so forth. It ends with K2n. Now ultimately what you can write? Kn1, Kn2, Kn3 and so on and so forth. It ends with Kn. This is the global stiffness matrix into the global displacement matrix. It is a column matrix with the elements Q1, Q2 and so on and so forth. It ends with Qn, which equals to the global load vector having the elements F1, F2, F3 and so on and so forth. It ends with F. Like this. Understand? Now, here I know Q1 equal to A1. It is a single known displacement. Right? Then, how I get the equations of equilibrium? Now, I get here n minus 1 number of equations. Okay? Right. Now, what you do is here, you can use elimination approach, the approach what we have discussed so far. How you eliminate the row and column? The row and column corresponding to this degree of freedom you have to eliminate. Therefore, the first row and the first column I have to eliminate. And remaining equations I have to write. So how you write? Again, see here, the size of this global stiffness matrix is now reduced to n minus 1. Now reduced to, size of this global stiffness matrix is reduced to n minus 1 by n minus 1. And size of this global displacement matrix reduces to n minus 1 by 1. And size of this global load vector reduces to n minus 1 by 1. Okay? Now, so how you write the remaining? Like this. A matrix having the elements K22, K23, K24 and so on so forth. K2n. Right? Next. K32, K33 and so on so forth. It ends with K3n. And ultimately, the last row, how we write? Kn2, next Kn3, and so on so forth ends with Knn. Remember, this is the reduced global stiffness matrix, or you can say reduced structural stiffness matrix into, right? We write here Q2, Q3, and so on so forth ends with Qn, which equals, again, what you write here? F2 and here F3 and so on so forth. It ends with Fn. Now, see here K21 into Q1, because Q1 equals to A1, right? This you have to take other side, minus K21 into A1. Next, second one. Second one. Next, minus K31 into A1. Like this. And ultimately, in the last one, minus Kn1 into A1. This is how we have to write. Okay? So using elimination approach, see how n equations are reduced to n minus 1. Now what is, the size of this matrix? N by n minus 1 by n minus 1. N minus 1 by n minus 1. And size of this Q? N minus 1 by 1. And size of this F? N minus 1 by 1. This is how the n number of equations are reduced to n minus 1 because one displacement is known. If two nodal displacements are known in the domain, then the number of equations are reduced from n to n minus 2. Okay. This is how we can obtain the equations of equilibrium using elimination approach. Understand? Right? Ultimately they appear in this form KQ equal to F. Next. Then what you have to do? You solve the equations obtained in the form of KQ equal to F. You get the nodal displacements. If first nodal displacement is known, right? After solving the equations of equilibrium KQ equal to F, you get remaining nodal displacements. Understand? If first nodal displacement is known like this, say Q1 equal to A1, after solving the equations of equilibrium, capital K into capital Q equal to F, right? You get the remaining nodal displacements, which are capital Q2, capital Q3, capital Q4, and so on, ends with capital Qn. Understand? Right. Once you get, the unknown nodal displacements, by solving capital K into capital Q equal to capital F, you can determine the element stresses using the formula sigma equals to Young's modulus into B into Q, where Q is the element displacement vector and B is the strain displacement matrix, E is the Young's modulus. Understand? Next. Now determining the reactions. Determining the reactions. So how you determine the reaction? Here we have discussed taking a single nodal displacement. Therefore, what is my problem? My problem is like this. There is an elastic solid with one end fixate. Other end is subjected to say force F. If this is node 1, Q1 equals to A1. Q1 equals to A1. Right? No doubt? A1 equals to 0. Now here, reaction you can determine. Under the action of the force F, what is the reaction here? No doubt F. But mathematically how you determine, that is the question. To determine the reaction, you can use like this. Take the first law of elements in capital K, right? That you multiply the elements of capital Q. Right? Then what you get? K11 into Q1 plus K12 into Q2 and so on and so forth. It ends with K1n into Qn, which equals to, on the right side what is there? F1. F1 plus R1. Then if you rewrite, you get the reaction at node 1. Reaction at node 1 equals to K11 into Q1 plus K12 into Q2 plus K13 into Q3 and so on and so forth. It ends with K1n into Qn minus F1. Understand? Similarly, the reaction at other support also you can determine. This is the procedure what we follow to determine the nodal displacements of the domain using elimination approach. So what we have discussed in this particular class, we expressed the total potential energy, introducing the global displacements, global stiffness matrix and global load vector, right? And we have discussed about the boundary conditions of two types. In the first case, the boundary condition, the case involving the single specified boundary condition in the first case. A case involving single specified boundary condition, and in the second case we have seen the multi-point constraints. Okay. So how we treat the boundary conditions? There are two approaches: elimination approach and penalty approach. So we considered the elimination approach, right? And we applied the elimination approach to treat a single specified boundary condition, say Q1 equal to A, right? And we expanded half Q transpose K Q minus Q transpose F. We put Q1 equal to A1. Then we extremize the total potential energy with respect to Qi, where I equal to 2 to n, right? And we obtain the equations of equilibrium. How many equations of equilibrium were obtained? N minus 1. When you solve them, you get the nodal displacements. Once you get the nodal displacements, you can determine the element stresses, element strains, and reactions at the supports also. Thank you. Thank you very much.